Hey, math people. We're looking at lecture 1 of chapter 1 of Calculus 1. So that's the first lesson. What are we looking at? We're looking at maybe opportunity to define what a limit is, some sided limits, defining that, graphical examples, algebraic examples, and then one today with like a little riddle thing, which will make sense when we get there. So this video was custom made for you, Alex. That was just a random name and a joke. The point is that use the timestamps and you can actually figure out how to make this video most efficient for you. Also remember that you can do this. Just be patient with yourself and utilize pause when you see the opportunity to do so. Okay, let's math. All right, consider 1 over x. It looks like this. Not like that, like this. Something funky happens at 0, and something funky happens if you go big. For now, that's all we need. If you want to play around with the idea of what f of 0 might be, and what f of infinity might be, neither of these things are actually things. So really what I'm going to do is I'm going to do some wrong math right away. F of 0 is sort of kind of like infinity, no? It's not. But like, isn't it sort of kind of like it if you go really high up, right? Likewise, f of infinity is sort of kind of like 0, right? It's not. But, you know, if you go real far, doesn't it look like it's going to 0? That's the whole point, is that we're really looking to create a tool that would enable us to say such answers. That tool is the limit. Here's how we write it. We say the limit as we approach, as x approaches, whatever your value of interest may be. Could be 0, could be infinity, could be some finite number, 2 or 3 or half, whatever, of some algebraic expression, and is equal to some number if we approach said number from both sides, coming in from the left and the right, because we're looking at a 2D graph. You only got those two little ways you can approach it. The big thing about a limit, if you can remember anything from today, is that it is a behavior. It is a behavior. It is not an exact value. We'll unpack that as time goes on. So if we really do want to unpack this as a limit instead, we can now actually make like actual statements on this. Now, there's a little bit of a little asterisk moment. We're gonna address it with approaching 0 because that's what we're doing today. But starting with lecture 2, we'll look at like what happens when we run toward infinity, right? Because you can never actually attain an infinite number of anything, but you can approach it over time. So looking at if we approach 0, well, we say that this limit does not exist, all right? If we have a different value coming in from the right and coming in from the left, clearly these do not match. We would say that that behavior heading towards 0 doesn't make a lot of sense. And it's because we have an infinite discontinuity here. If you remember the phrase asymptote, maybe that's how you maybe first saw it. That creates some confusion. So right away, we're starting with a limit that doesn't work. Don't worry, we'll do limits that make sense numerically very shortly. But if we approach infinity, we now can say 0 to something like this. Because never do we ever actually attain the number 0. But we get really close. So close that if we approach infinity, we just get as big as we can, whatever that means. We can say, hey, the approaching value is 0, yet we don't ever actually quite attain it. All right. Let's look at something like 2x squared minus 2x, so a little different, right? And then all over x minus 1. Here's the thing. Sometimes you can just plug and play. If I just pick up this 0, place it into this expression, I get like 0 over negative 1. That just works out to be 0. I'm going to show you a graph in a second. But then sometimes you can't do that. Sometimes you attempt to plug in 1. You get 2 minus 2 all over 1 minus 1. And that's a problem. However, observing like the graphical behavior could help us out. So without revealing the answers right away, I'm just going to go ahead and graph this 2x squared minus 2x all over x minus 1. Looks like a line. It's not a line because we got a little tricky guy right over here. If you plug in 1, which would be the exact value and not the behavior, you get what's called an undefined solution, we'll just say. It's undefined. You cannot compute f of 1. However, you can observe that coming in from the left and coming in from the right, we get really close to like, I don't know, what is that value? 1.94, 1.96, 1.99, and then undefined. And then coming in from the right, same story, just above 2. So, using that intuition, okay, you can directly plug in 0 because it's continuous at that point. And there's no issues with the limit and the function being evaluated at 0 being the same number. In fact, that's how we define continuity, at least in this class. And with the other one, you had to be a little crafty here. What you could do is you can factor out a 2x. The x minus 1's cancel, and if you then do a substitution of that 1, you get the value 2. So sometimes algebraic manipulation can help us in solving these limits algebraically. Viewing this graphically, it's clear it's approaching 2 from both sides. Doing this algebraically, you got to know algebra. Who would have thought? All right, so sometimes approaching from a side has utility. So this graph right here, absolute value of x over x, I didn't know what it looks like when I first typed it out. It looks like this. You got just 1 on the right side and -1 on the left. Just play around with some numbers, that'll make sense. We'll say that if we approach 0, that limit does not exist because we're approaching -1 from the left side and we're approaching 1 from the right side. Those don't match. Limit doesn't work. However, can we maybe create like a sub-definition that would help us quantify the, sided behavior of it? And the answer is yes. All we do is we just slap this little minus sign as a superscript of whatever you're approaching. So in this case, it's 0. So we put a little negative here. And that's a way of saying from the left, from the negative side. And then for dealing with coming in from the right, from the positive side, we plug it, we place like a little plus power, it's not a power, it's a superscript, next to the value you're approaching, 0. So like this, right? If we were to consider what this graph may look like. So another example, before we get to the meat of it all, right? We're still kind of talking about it conceptually. We have a piecewise function that is an absolute value all the way up to 1, so over here, and then it's just going to change to a flat line of 2 thereafter. So if you'd like to pause and try it out, feel free, but I'm going to just kind of storm through this beginning part before we get to the real examples here. Looking at what this graph looks like, here's kind of what I was trying to describe. It's the absolute value on the left side of 1, and it's a horizontal line on the right side of 1. So this is a jump discontinuity, by the way. So the last one also had a jump discontinuity. So as of right now, we actually know 3 discontinuity types. We know infinite discontinuity. We know a removable discontinuity. It's a hole in the graph. It's hard to see, but it's there. And then we have a jump discontinuity. You can go from like, a 0 slope to a 0 slope, or you can go from a slope to a 0 slope. It doesn't quite matter, so long as the values just are off by, some finite amount. Anyways, looking at the solutions here. Coming in from the left, it is clear we are approaching the number 1. Coming in from the right, hopefully. So it's like, I like to say these things are simple, but not easy. It's simple to see that coming in from the right side, you get 2. It doesn't make it easy, right? You got to have that little click moment, and that comes through practice. And we see here, okay, well then what's the general limit? Just approaching 1, right? Not from a side. It doesn't exist because we're 1 from the left, we're 2 from the right, and it turns out 1 is not equal to 2. So can't say that limit exists. All right, so like what is the difference between limit as you're approaching it at some value, 2, 3, whatever it is, and like actually computing the function at that number? So what's the difference between the limit as x approaches 2 versus f of 2? Those are very different things. So here's kind of how I would compare them. You can have a function as defined and the limit existing. When these happen to be the same thing, that's when they're connected and continuous. When they're not the same thing, you get this little weird gotcha moment where it's like a floating point and like a different limit value. Because consider how the limit here exists to be whatever this output is. Maybe it's 3, where the function is defined as 4. So a little tricky, doesn't happen very often, but it will happen in the landscape of limits just to try to trick you because we're evil. We have a dark pit in our soul, calculus teacher, sorry. But if we're looking at like, an undefined value, okay, but then the limit exists, that's how you get your classic hole. We looked at this scenario. We looked at this one as well, the jump. If the limit does not exist, aka you got a different value coming in from the left and coming in from the right, then the function is, it could be defined. Like here you see it's kind of filled in here. The function is defined as whatever this output is, not this whole. But the limit does not exist because you have a different value coming in from the left and right. Whereas if you look at the final case, the infinite asymptote, there's other ways of creating this, but here's just one example. You have an undefined value here because it's an asymptote. Perhaps you get like, 5 over 0, which is, not a defined value. And then the limit doesn't exist because the value does not match coming in from the left, coming in from the right. The approaching value, we should say. So the big thing is that you walk away with this understanding that the limit has to do with the behavior, and then the value has to do with the exact what's happening at that moment. So here's a graphical example. Feel free to pause if you're like, okay, I got this. Run through it. I'm going to go through it in 3, 2, 1. Bam. So I'm going to go over the answers. Hopefully you paused there, or you just panicked and went back and then tried it, and now you're with me again. Whatever. All right, so looking at -3. If we come in at -3, we got a jump discontinuity. That's no good. Does not exist. However, if we compute f of -3, that's just 1. Filled in circle there. If we're coming in towards -3 on the left side, that's also 1. But coming in from the right, positive side, that is -1. You can see here that if we approach 1, that looks like a suspicious moment on our graph, but it's not. It's just a cornery looking thing. It's continuous there. So we have both the limit and the f of value as the same thing. It's continuous at that moment. So the limit and the exact value are both -1. Approaching 2, we see a removable discontinuity, and we see that floating evil point there. That's the kind of artificially created case of trying to get you. So the limit exists to be 1 because that's what the graph is approaching from the left and right side, but f of 2 is 0 because you got that floating point right at an output of 0. All right, we didn't talk too much about like the difference between does not exist and infinity. Can you say infinity is a solution when it's not a value, it's a concept, not a number? The bottom line is to this, anytime you think the answer is infinity or negative infinity, those are not finite real numbers, and therefore those do not exist. You can use does not exist in those scenarios. However, I like to be a little bit more descriptive, and if it does approach infinity, for example, in this case, we're coming in at 3 from the left side, going up, it's run into infinity, just fenced off by this asymptote. That's infinity. But you can also say does not exist. Likewise, if we're looking at it from the right side, we can see we're going down forever, and in which case we have approaching behavior of negative infinity, so it just does not exist. So either or. This one, you don't got a choice. You got to say does not exist for the total limit. You're coming in high, coming in from the left, and coming in low, coming in from the right, and that just doesn't match. The last one is cut off. So here's your moment. We now know the difference between does not exist and undefined. So really hold yourself accountable to this last one here. What do you think? Is this undefined or does not exist? Can I move me on? Yeah, I can. Ta-da! It's undefined. So we use this language of undefined talking about the exact values, and we use this language of does not exist when we're talking about behavior. So I'm going to move myself back. Limit does not exist. Value, we say undefined. All right, algebraic examples. Feel free to pause. 3, 2, 1. Here are some solutions. If you have a continuous function like the parabola, you can just plug in. It's called direct substitution. You get the number 8. If you get okay, so this problem has an issue. It has 2 asymptotes. It has an asymptote at negative. You just got to factor the denominator and see what doesn't work, right? What would get 0 in the denominator? It has an asymptote at -3 and an asymptote at -2. Neither of those are issues for 3. So if you plug in 3, you get 9 minus 9 up top. It's 0 up top, which is fine. And then you get some other number down below. I don't know what you get. You get 9 plus 15 plus 6. That's too much math for me. So you get 0 over some number, which is just 0. For the second case, we start to encounter some issues. If we, and this will be a fun one to look at graphically, if we directly substitute a -3 in, you end up getting 0 over 0, I think. Right? Because -3 squared is 9. Minus 15 is -6, and then -6 plus 6 is 0. And up top you get 9 minus 9, which is 0. That's a problem. 0 over 0 is not a thing. We don't know what it is. And actually, it doesn't know what it is. It's called an indeterminate. It can't decide or determine what it is. So we actually have like a whole chapter in this class where we address situations like that. But that's not the point of this. This chapter is really just the early bird special to what calculus is. I call it the road to calculus world. We're really not in the theme park yet, but we'll get there. So what's really happening at -3 is this. As you may have expected, it is a whole. Hello? Hello? There it is. It's undefined. But through algebraic manipulation, we can actually factorize top and bottom, and you see that the x plus 3's cancel, which was the bad guy, right? -3, you plug that in, you get that 0. So after that, you can plug in the -3 just fine, you get 6. And hopefully that makes sense graphically as well, because, take a look at where, 6 is right here, right? So you can see here, these values are very, very close to 6. Go math. All right, round 2, 3, 2, 1. Here are the solutions. Hopefully you paused. All right, so we did not have a problem with 0 over number. We definitely have a problem with number over 0, like non-zero number. So if you try to plug in 4 here, that's no good. You get 4 over 0, and I don't know what that is. Actually, I do. It's undefined. So can't do that. Turns out there's actually an asymptote there if you wanted to look at the graph. It happens to approach it from the left and right. So you could say infinity, but you could also just say it does not exist. That's also fine. It's less work. All right, and then for the next one, I just flipped it for fun. 0 over 4 is fine. That's just 0. This next one's a goofy case. There is a little moment within the first chapter of limits where we try to throw some razzle-dazzle at you, and we say, hey, do you remember the conjugate from Algebra 2 with imaginary numbers? And you say, what? And that's what you need here. So if you attempt to plug in 4, so think about it as like another algebraic manipulation. It's just like kind of like factoring. I actually had a student that factored. Oh, that was like mind-blowing to me. I was like my 5th year teaching, and he told me, he's like, why can't I just factor the denominator to square root of x minus 2 and square root of x plus 2, and then cancel out the square roots of x minus 2s? And I'm like, whoa, that's actually smart. But anyway, so the way you're supposed to handle these like square root cases, I guess. Okay, sniff it out. I see the square root. You're going to need a conjugate here. It's really just taking this sign of minus 2 and making it a plus 2. Conjugates with imaginary solutions, they come in pairs, like a plus bi, a minus bi. You don't need to know that stuff, but this is the last little trick we can do to you. It'll show up once on your test, maybe. And you multiply it out, you end up getting the x minus 4 up top, which is great, because if you don't multiply out the bottom, those just cancel, and then you can do a direct substitution. It's a little bit of a trick, but it's like the one little thing we can do to you. That's a little mean. Anyway, the rest of these, give them a go. 3, 2, 1. I'm going to show the solutions now. Okay, if you know the graph for tangent, you'll know that there's an asymptote at pi over 2. So that does not exist. You can also write this as like sine over cosine using the, quotient identity. You would get 1 over 0, and that's undefined. So you're like, this is suspicious. But the graph, sometimes you have to think about the graph, bottom line. I tried to be tricky here. This is actually just a direct substitution. Cosine of 0 is 1 and e to the 0 is 1. So this is just 1. This is just continuous. There's no issues here. The last one is goofy. I don't like it at all, but some teachers may make you memorize that sine of x over x if you approach 0 is 1, and this is kind of what happens with the graph. I think it's a waste of time because we eventually learn the skill that handles these anyway. So I don't know. I don't make my students memorize this one, but maybe you have a teacher that does make you memorize it. Sorry, it's just how it goes. And by the way, Khan Academy has a nice flow chart on how to handle these algebraic cases. So feel free to check that one out as well. Okay, tabular example. This one's just like kind of commonsensical. Let's just assume f of x is continuous. If you have this data, or actually no, I don't need it to. It's not continuous. What am I talking? It's not literally undefined at 2. It's a hole at this value. What are we probably approaching, right? If we're coming in toward 5 on the left side and we're coming in towards 5 on the right side, the limit's equal to 5. If you saw something bizarre like 4.9 repeating on this side, and then on the right side you saw like 6.01, it's like, okay, that's not going to match. Here, they match. All right, the last one. How fast is Lightning McQueen going? The answer, it's 0. Okay, I actually just wanted to include this picture because Lightning McQueen Crocs are a thing, and that shouldn't happen. But anyway, okay, so this is where the limit comes in handy. What is the exact speed at this singular instant of when this snapshot was taken? He's not moving, so is it 0? The answer is obviously no, because movement is possible. So what we need is the behavior, the study of the behavior. So the limit helps us build this idea of what the derivative is. And that's the course that you're in. You're in differential calculus, I think, right? Or you're watching this for fun, in which case, go you. That's all for today. Math On.